I don't know whether I should thank you without reading it first. What you
exactly, you don't know whether you should thank
you. Maybe I should change my name afterwards.
Maybe you should change your name after. It's a cover.
Oh, nice, nice. Well, I'm honored.
Okay, I think we can start now. So before I introduce our speaker today, let me say that, make a small announcement that we have the program for the next series. So the seminar after this one is going to be Richard Healey on the 7th of January, talking about are facts relative in a quantum world. And then we will have Liz Mollin, Stephen Wolfram, Doreen Fraser, Laurent Friedel, and Alex Kissinger. You can see the program on the website on qiss.fr, and we will also be sending announcements to the mailing list. So it is our pleasure to have today Časlav Brukner. Thank you, Časlav, for accepting the invitation, who will be talking to us about the quantum superposition of opposing thermodynamic hours of time. It's a paper that is on the archive with the authors here on the introductory screen. Časlav, I remind that the format is usually we suggest about 30 minutes to leave a lot of time for discussion. We will not cut you if you run over time. Yeah, and you can start.
Okay, well, good evening, at least on this side of the globe, to everybody. And thank you, Marius and Pierre and Lucas for the invitation, also for keeping the community together. Today I will talk about time, just to continue the tradition of the last talks, and also the very last one of Lucien Hardy. It's a work that has been done together with Giulia Rubino, who is a PhD student in Vienna, about to finish in experiment and theory, and Gonzalo Manzano, who is a postdoc and Erwin Schrödinger Fellow also at Vienna. So I should also kind of excuse myself if you are like Carlo to hear this talk for the second time. Giulia presented this a couple of weeks ago at the Perimeter seminar, but sometimes, at least this applies for me, it's very useful to think and to hear something maybe twice or multiple times, and to get maybe some new thoughts about the subject. Let me start with a kind of a remark. I see quantum theory not only as a new theory that extends the range of parameters that we can test and predict, but it's also kind of a tool with which we can think about what all possible notions of classical physics should be revised. And the methodological tool for this is usually related to various no-go theorems like Bell's theorem or Hohenschwecker theorem. And indeed, we are used to apply these tools to what we call observables. And although it's of course a matter of interpretation to a certain extent, for many of us, it's true that we can say that observable position or momenta should not be considered as having predefined values before and prior to observations. And recently, we tried to extend this to something which is traditionally considered as to be well-defined, even in quantum theory, as the causal order. But even there, we can think about situations in which we can put causal order in superposition and eventually apply these methodological tools to say that the nature of the causal order, even in quantum theory, is not the one that we know from the classical physics. And so the message of this particular talk goes towards time, because time so far has evaded such a characterization that I just explained, introduced proposition, momentum, or causal order. It has a certain objective status in quantum theory. And the question is whether we can extend this also to the notion of time. And I don't have an answer to this in generality, for the reason that we have many different definitions of time. But what I'm gonna concentrate on in this talk is the thermodynamical notion of time. I will try to argue that we can have quantum indefiniteness with respect to the thermodynamical error of time. And it does share a similar features as the observables that I mentioned before. So this is the message of this talk, and methodologically, we will show this by really explicitly superposing thermodynamical processes with opposing errors of times. When I think about opposing errors of time, this means that when we think about the error of time thermodynamically and identify this with the increase of entropy, what we will do, we will impose processes which have opposing sign of entropy change. So here's the overview of the talk. I will still be for some time concerned with motivation. Then I will spend a considerable amount of time to introduce the background information in form of fluctuations theorem. Then I will introduce our new results, which should give a signature of the superposition of thermodynamic error of time. And here I would like to concentrate on two specific results. Even if we have such superpositions, how do we effectively then have a sense of a definite times error in quantum mechanics? And finally, I will go into a genuinely quantum feature of interference effects due to this superposition. And this will be shown in a certain distribution, so-called work distribution that has no classical analog. It's interesting to mention that this work also has some practical implications. For example, we can think about not only superposing thermodynamic processes with opposing error times, but we can generally superpose different thermodynamic processes that are run by thermal machines. For example, a refrigerator and heat engine. And I will just comment by the end of my talk about this practical side of the research. And finally, I will conclude and look and give some outlook. So the way how I like to think about directionality of time and thermodynamics is something what was put by Jaczynski. People who are active in quantum thermodynamics, they know the name Jaczynski from the Jaczynski's inequalities. And in 2011, he introduced this time directionality game, and it goes like that. Imagine that I record the motion of a non-equilibrium thermodynamic process, and then I toss a coin, and depending on the outcome, I either play the movie as is in reality, or it's time reverse. And then you should guess in which order the movie is played. And now I give an example. Imagine that you have a vessel with gas in it, and let's say it's concentrated in the left part of this vessel, in left half, and then we let this gas expand, and after a while see that the gas in the last frame of the movie full the whole vessel. Now we tend to say that this is a process as we see this in nature, and we will say the film, if it's shown in this order, corresponds to the real process in nature. However, the opposite one, in which we at the beginning have a gas filling the whole vessel and then spontaneously concentrated to the left-hand side, the left half of a vessel, is something which is not very likely, and we tend to say that the movie was shown in the reversed order of the one that is realized in nature. What we do here is more formalized, is optimal guessing strategy for a macroscopic system. And there we say that if the work performed in the system by the external driving mechanism, which is here W, is larger than delta F, which is the difference in free energies at the beginning and the end of the movie, we will say the movie runs in the right order. And if it's negative, if it's smaller than the difference in the free energies, we will say the movie runs backwards. And it turns out that this is the optimal guessing strategy. And whenever we have this sharp difference between the left and the right-hand side of this inequality, we can say that we have a well-defined notion of the thermodynamical error of time, which is true for the macroscopic system. Now, the other way to say the same is to use the thermodynamic entropy, which is just the difference between the work performed and the free energy difference, and multiplied by beta, which is the inverse temperature, 1 over K Boltzmann constants time temperature. We can talk also about entropy, positive or negative entropy, instead of the work and the difference in free energies. So I will interchangeably use either the right-hand side or the left-hand side in, in discussing the directionality of time. Now, if we zoom in the picture that we had before, to that extent that we see individual molecules, and we actually don't have any idea about initial configuration of the entire gas, and we don't know whether the gas fills the whole vessel or only part of it. It seems that both movies shown, when we are really focused or zoom in into individual scattering molecules, that both directions of movies are equally probable. And we say that for a microscopic system, the thermodynamic error of time is not well defined. Here, I would say that micro and macro should be understood in a sense, not only as the size of the system, but always with respect to the thermal fluctuations, which are order of the Boltzmann constant time temperature. Now, how can we really quantify this, both the game and the notion of the directionality of time? This is done by fluctuations theorem. And I will here introduce the most simple version of it that is sufficient for our purposes. What you see on the left-hand side is a slightly adapted example that I already introduced. So we have a gas that at the initial time is in a left half of the vessel. Then we have pulling out the I'm now confused. I forgot the name of the. We push and pull out the thing. Sorry, piston. Thanks you. Yeah, I lost track. The piston. So we pull out the piston at the halfway time. We see the second picture, and we pull out the piston until the end of the vessel, and we can do it relatively fast, such that most of the molecules are still in the left-hand side. This pulling out the piston is actually the specific quench, which we model here by a unitary transformation on the system alone, because we do it relatively fast, such that there is no thermalization and connection with the environment during the quench. And so we start on the right-hand side, you see initial state, rho S0, we put some work into this quench, we come to the unitary evolved state at time t equal tau, and then afterwards, and that's the change from the third to the fourth picture, we let the system thermalize again with the same temperature, arriving this state that I show here as rho S0 tilde. So what we see on the left-hand side is a typical sequence. Of course, it could be that we do not go through this typical sequence, but this is the one with a high probability to be realized. Now, the question first arises like how much work has been invested and how to quantify this. And we know that in quantum mechanics, we should not make a mistake and talk about quantities without really having measured them. And so what we usually do is we measure energy at the beginning and at the end of quench, and out of the difference from this energy, estimate the work invested. This is known as two-point measurement scheme or TPM scheme. So what we do, well, we have at the beginning measurement of the energy at the end, and I define the energy values that we observe that as En0 and En tau. And out of that, we can construct the difference and the stochastic work, which we call invested in a single realization because it depends really on the single outcomes that we obtained. But now we are interested in the probability to get always work invested W. And so therefore we have to sum up over all these individual results that always corresponds to the same W value. And we weight this sum with probability that the single realization is realized. So what P and M is just a joint probability to get the result N at the beginning and M at the end. And this joint probability can be written with the Bayesian rule as the initial probability to get the result N. For example, if initially we have some Gibbs distribution, this can correspond to some Gibbs distribution. And then conditional probability, which is written here, once we get the result En, unitary evolve, and then get result Em. Now, to state the fluctuations theorem, we need also to consider the so-called backward process. This is only a name for now. A backward process is the one when we start with the end state of the forward process. So here we state with the last equilibrium state of the forward process, and we introduce the backward quench, which is a time reversed quench of the forward quench. Therefore, we push the piston inside the gas. And what I draw here is again a typical sequence in which, for example, half of the molecules are hit by the piston and move towards the left side of the vessel with certain velocity. And we stop at the halfway through. So we leave the gas in the left-hand side of the piston and let in the fourth picture equilibrium work. We interact with the thermal bath and let thermalize the state. And that's why we, after the quench, go back to the initial state of the forward process. So again, we can also in this backward process compute what the work invested is along this process. And the situation is very similar to the forward process, with the only one difference is that if we get exactly the same result Em now at the beginning of the forward process and En at the end, then the work that has been invested is of the opposite sign as compared to the one in the forward process. And now let's go back to our game of time directionality. When I say we see a movie, yes?
I'm confused. Sorry, I got lost.
Yes.
If maybe I missed something. You're reversing the microscopic dynamic of the macro. I mean, if I pull rapidly the piston, the work is 0. If then I thermalize and I push, the work is positive.
Yes.
So it's not the same work, and I don't go back to the
same work. It's not the same work. At the moment, you can think about forward and backward processes completely independent from each other. So they are conditionally called forward and backwards, but these are at the moment completely independent of each other. Now, in the next slide, I will consider only those cases where I have the same work performed by the opposite sign. Then I will connect them. So far the slides were just to introduce different processes, and the work.
Unrelated processes so far.
They are not related yet.
Okay, so
they are not related yet. So I think the next slide, and if anything is unclear, please let me know. I think the next slide will explain exactly your concern. And so here I put two processes next to each other and go back to initial motivation. And now instead of thinking about a continuous move, let's see that we have just 2 shots of this movie. This is the first one and the second one. And you see that both are the same in the left and right process. So imagine that you only see the first one and the second one. And then you ask yourself whether these 2 red squares that you are shown came through the physical process that was the forward process over the backwards process. So now you see that I compare the 2 processes in which work, the amount of work, independently of the sign, the amount of work is the same, but in one case it will be extracted, in another one invested, depending on the sign. Now, the question is whether these 2 red squares arise from the forward or backward process. And now when I put inside the value of the work, then it is the fluctuations theorem that I will introduce in the next slide will give you the ratio between these 2 probabilities. And if the ratio of probabilities, for example, as shown in this picture, and it is true, that probability for a forward process is much larger than probability for backwards process, then I will guess it was the forward. And indeed, if you look now the forward process, it's something which is very natural. We pull out the piston and the gas expands. Then the other one is very non-natural. Well, we in the first picture here, we already starting from the bottom picture to the first red picture in the backward process, we see that the gas spontaneously concentrate on the left-hand side, which is low probably. And therefore, in this case, I will have this ratio between probabilities, which favors forwards process, and I would say the left process is the one which happened in the reality. Of course, there is nothing particular about forward and backward, because I can also have the following situation. In the following situation, the probability for the backwards process is higher than for the forward process. Why? Because what we see here on the right-hand side is a typical realization of backward process. I push the piston inside the gas. We already saw this picture. And then I will hit some molecules and they go towards the right-hand side and then thermalize. The backwards of the backward process, which I call the forward process, is not likely to happen, because what here we have is spontaneously, we have the molecules that get some velocity on the right-hand side and then push the piston, and I pull also the piston away from them, and then they thermalize again. So in that case, the ratio of the 2 probabilities will be the opposite as the one that I had before. And I would say, well, backwards process is most probably not forward. I would say the typical realization is something which happens in nature. And I will opt that this is the one in which the movie is shown according to the order that we have in the nature.
Professor Brukner.
Yes.
I just wanted a clarification. Do you assume that the state starts in a thermalized state
Yes,
and ends in a thermalized state?
Yes, they start and end in thermalized state.
So in this case, this is not the case in this diagram, right? Where the particles are shown that they're already moving in one direction or the other.
No, look, the first and the last picture are always thermal states.
Right, but the measurement...
Move, this is already the second picture.
Yes, but the measurement is... I thought the measurement was taken at the end of the process, like after the...
Well,
the unitary...
Yes, yes, it should be... Okay, so this third picture, it's better to the end will be really until the end, moving out.
Right, at the very moment it ends.
But why I did it is that I copy-paste from some other papers. Okay. I was too lazy to draw the new one, but the correct one will be that I pull out the piston until the end, and they still move towards the piston, and then the last one will be exactly the thermal. So this is a little bit before T equal tau.
I see.
But thanks for the question.
Okay. Thank you very much. It was useful.
Okay, so these two cases are just extreme cases of the more general statement of the fluctuations theorem, which connects two probabilities, namely the probability that a work W is invested along the forward evolution, which is P plus W, divided by P tilde minus W, which is the probability that the work minus W is invested along the backward evolution. This ratio is actually given by so-called dissipative work, namely just the difference that we had in the macroscopic case, difference between the work invested and the difference in free energies. And the previous cases were just extreme cases where this dissipative work had very large positive or negative value. And now, if this dissipative work is zero, we standardly call processes reversible. This is when the two probabilities are the same. So indeed, then in the game of time directionality, we cannot do better than randomly choose. If this is not the case, we talk about irreversible process. An alternative way to formulate this is in terms of thermodynamic entropy. And the ratio is then the probability of an entropy increasing in the forward evolution and the probability of entropy decreasing in the backward evolution, which is then given by this exponential function with exponent being the difference in entropy. And something which I am not able to show here, but if you think about single shot, when you just get the results N and M, it's natural that the definition of entropy is given very similar to the thermodynamic entropy, but it turns out that at the same time, this is also given as the logarithm from the ratio between the probabilities to get the two outcomes in forward and in backward process. And this is a kind of a measure of distinguishability between the forward and the backward process. So basically, this can be understood as some kind of measure of how different these probabilities distributions are. And therefore, if there are no differences between them, we are back to delta S equal to 0 and the case where we have reversible process. This ratio can be just simplified. This is the second expression as a ratio between initial probability distributions in a thermal state in a forward and backward process, just because the transition probabilities in the two cases is the same. And now I'm coming to how we should guess in general in the time directional. What you see here is a likelihood function as a function of dissipative work. And what you see as a green line, which is a step function, a theta function, is the classical kind of, or what, if you want, macroscopic guessing strategy. As soon as dissipative work is positive, you should, with probability 1, guess that the shown movie corresponds to the order in reality. And the opposite if dissipative word is negative. But however, if you have kind of intermediate case where you also have thermal fluctuations, then your likelihood function, which is given by the fluctuations theory and by Bayesian reasoning, is given by this orange curve. And so you have certain area of the, or region of the blurred thermodynamic error of time where you cannot know with certainty whether the movie was shown in the right or opposite order. And this area increases as the temperature increases. That's something which is also in line of our understanding. Now, to sum up this background information, we can say that when beta times dissipative work, which is the entropy change, is the order of 1, the directionality of time cannot be inferred, and we will make some errors always. However, if in absolute value, this is much larger than 1, we can then say whether we have one or the other process in place. And now I'm coming to the actual results. What we will think about is whether we can have even quantum superposition between opposing directions of time, thermodynamic directions of time. What would be this? So for that, just to remind you that these forward and backward processes were only colloquially called forward and backward, but they did have certain property which is interesting, that when I see a very large entropy change, it can only be in agreement with one of the two. So if I have a one value measured and entropy change, then I would say, okay, this must correspond to one of them, but not the other one. And therefore, they do have opposing variations in the entropy and opposing errors of time. And now what I want is to superpose them. Now, many questions arise. Well, how to do even, how to think about, if you want even thermodynamic processes in superposition, there's a very often very mixed states that and processes. So how can we even formalize this idea? And then once we formalize this idea, how then a well-defined thermodynamic error of time is really established? The one that we see in nature, even if we would assume that these superpositions are valid possibilities, then what would be an operational signature of this superposition? How would we actually convince somebody that we have prepared such superposition? And finally, is it useful for something beside a very interesting contemplations about the nature of time? Is it maybe useful for some practical purposes? And so I'm going now to introduce the framework to answer these questions. So what we see here is that I would need to have 3 subsystems to describe this. One will be the system under investigation, that is the thermodynamic system. Then I would also introduce purification of it, which is environment. And environment can contain all possible degrees of freedom that are necessary to purify the possibly mixed thermal, for example, state of the thermodynamic system S. So it could be a thermal bath, but even more than that. And finally, I will have an auxiliary system that will control the evolution, and you will see in which sense. So initially, I will prepare the state that you see here on the slide with some amplitude alpha 0 and alpha 1 as complex numbers. And these two states are chosen in such a way, psi 0 and psi 0 tilde, that they are purification of the thermal state. The psi 0 is the purification of the initial forward process and state, and psi 0 tilde is the purification of the initial state of the backward process. So if you see then now these two states, you see that there's a pure states which are entangled between the system and time and environment. And the amplitudes in the entanglement corresponds to the Gibbs distribution of the thermal states. So when I trace out now environment, then I get exactly the mixed Gibbs state for the system. And Z, 0 and tau are statistical sums, partition functions. And I have a situation fully analog also for the backward process, with a small difference that in the backward process, I also have this theta, which is an anti-unitary time reversal operator, because I have to reverse entire evolution and the states in the backward process. Now, this state will be then subject of a superposition of quenches. And 0 and 1 are actually auxiliary states that will help us to control these quenches. So if I have auxiliary state in 0, then the unitary that is applied is the forward unitary in the forward quench applied on the initial state for the forward process. But if the auxiliary state is 1, then I apply the time reversal quench on the initial state of time reversal process. And as I said, during the quench, the system will not interact with the environment or thermal bath, but after the quench, just like in a non-quantum case, the system will thermalize through the interaction with the thermal reservoir.
Časlav?
Yes?
One question. So with respect to the piston example, should we think about this like having the piston in the middle and U is like pulling it on the right, U tilde is like pulling it on the left?
No. Okay. With respect to the piston, I would say, let me go to the maybe some of the pictures. I would, sorry. So I would say you have a certain auxiliary state that could be in two possible orthogonal states, and we will apply the conditional unitary. The conditional unitary will be applied on the system such that when auxiliary qubit in 0, the piston will be pulled out. When the auxiliary qubit is in the 1, the piston will be pulled in.
Okay. Yeah, thanks.
Welcome. Okay, so so altogether, now we apply on this superposition of two thermodynamical processes the two-point measurement scheme. We want to know how much work we invest in this process, but in order to do so, we need to extend this two-point measurement scheme, and that's the extension here. You have the illustration basically of the map that we will apply to this superposition in order to find out how much work has been invested. So here it's an illustration about auxiliary system, that is the path takes the role of the auxiliary system. So you have a beam splitter, and auxiliary system could be in a 0 value. If it is in a 0 value, we will go on with the forward process. We will measure the system before the quench, we will make a quench, we will measure again after. And if it is 1, we will observe the initial state of the backward process, where we obtain the same result as here. So these two boxes, although they are drawn here as two boxes, should be a single box. It's a single result. There are only 2 results, not 4 results in this process. So this is the same result as the last result of the forward process. This is the initial energy of the backwards process. Then we have a backwards quench, and then the final result of the backward process, which was the initial result of the forward one. And then, in order to obtain a real superposition, we have to forget which path information.
Sorry,
I just finished the sentence. I give you, I just finished. We overlap on a beam splitter, and then after the beam splitter, we measure the auxiliary qubit. So after the beam splitter, when we get the auxiliary qubit in plus or minus, we don't know anymore which path the process took. Otherwise, before the beam splitter, we could take measure in 0-1 basis and find out whether it is forward or backward process. Yes, Carl.
When you say we measure and we obtain this number, do you mean you select the case when this number is obtained, or you select the runs where this number is obtained?
No. I mean, no, you get sometimes, I mean, there are just two results, and it could be any number, M and N, any combination M and N. And I don't select. I measure, I get an M result, then I prepare the experiment once more, and then I measure another pair of M and N. And eventually I will collect them to get some statistics.
So you just, okay, so you're just interpreting it differently because in one case you have U, in the other case you have U tilde.
Yes.
Okay, got it.
So here's the mathematical description of this illustration, which should not be maybe taken too literally. So what we see here is exactly the same. This map is whenever you have a zero auxiliary state, and then you measure En, then you have a forward quench, and then you measure Em. And whenever the auxiliary qubit is in 1, you have time reversal Em state projecting on this state, then backward quench, and then time reversal projecting on En. And we want to know when the W and M is always have the same value. This will be, so this map will measure us how often or the cases when we invest W work in this extended 2-point measurement scheme. So very similar to the previous case, of course, with a big difference, there is a superposition now. Okay, and I said that after that we need to project on the second beam splitter in order to obtain the real superposition between two processes. And so here, what you see is that after applying this map MW, we need to project the auxiliary qubit. And I will say that we cannot project on an arbitrary state Xi, although later on, this will be always a superposition basis. This Xi will be always something which is 0 plus minus 1. We want to forget whether this is a 0 or 1 process. So I apply this projection after the map, and then get the joint probability of measuring the word W and projecting the auxiliary state onto Xi, which is just the square of this state. But what I will be interested in is a conditional probability. Once I obtain either plus result or minus result, I want to see what is the distribution of the work. What is the probability to invest certain amount of work, W. And then I need a few more notation for the few more quantities, just to express later on in easier way the results. So what you see here is Q0 Xi and Q1 Xi as certain values between 0 and 1 and have interpretation of some weights or some probabilities. And their actually physical significance is clear from the following equation. What you see here is exactly the work distribution for the result Xi. So you see that there are 3 terms. The first one reminds us on the probability distribution of the forward process, the second one of the backward process, and there is something which is interference term. This interference term looks quite complicated. It's really not relevant to understand every single thing. But maybe what is important is that also decreases exponentially with dissipative work. Roughly, I would like to see this expression as a combination of two types of terms. The first one is incoherent part, which is really compatible also with having a classical mixture of processes in one or the other direction, weighted with Q psi 0 and Q psi 1. And then there is a coherent part, which is truly coming from the superposition of two temporal directions. Now, here, finally, we have all the formalism that we need to state our results. So the first result was how a well-defined time directionality arises in this situation. It turns out that if you measure the dissipative work or the work invested, and out of it you estimate dissipative work or entropy, and if the value of the entropy is large value, much larger than 1, then the probability distribution for the work boils down into the one of the forward process. Mathematically, this is because we have exponential decrease with the dissipative work, both for the probability in the backward process and the interference term. And so what we obtain is the state of the system, which is projected in the forward component of quantum superposition. So this will be similar as if we would take the superposition and project on a zero auxiliary qubit zero state, which was specifying the forward process. But here is interesting thing is that we do not do that. We just measure entropy. And by measuring entropy, we effectively project the system onto the forward time error. And similarly, if we have a very large negative value of the entropy, we can show that we project the probability distribution is then effectively the same as if we would project on a backward process, namely on auxiliary qubit in state 1. So in the sense, we recovered a well-defined directionality through the measurement process of entropy and assumption that we get a large value, absolute value of this entropy change. Now, what remains to be investigated is what happens if we have that this change of entropy is of the order of 1. And this is the case where we actually have interferences. Then classically, this is the case where you cannot distinguish between forward and backward, but here is not only that we have equal probabilities of forward and backward process to happen, but also we can have interference. And in order to show you, I take an explicit example, a spin 1/2 particle that undergoes a certain quench or time-dependent Hamiltonian. And this is a time-dependent Hamiltonian. It's just in a magnetic field, we have a spin 1/2, and the direction of this magnetic field is within XZ plane, but rotates with some constant angular velocity omega, large omega. And I have also a small omega, which is the energy of the spin 1/2 particle, order of the energy of the spin 1/2 particle itself. And so I will just do the same what I have done before in general. So at the beginning, I have a Hamiltonian, which has at t equals 0, it's just proportional to sigma z. So I have spin up and spin down. And at the end, at t equal tau, at the end of the forward process, the eigenstates are eigenstates of sigma x. So they are, so to say, complementary, diagonal. And I also have just two possible energy values, which is 0 and h bar. And what I do is, well, I do a superposition between the forward process and the backward process. And in this special case, the difference in the free energy is 0. So really, entropy is proportional to the work invested. So I supposed what I have supposed before, that I superpose these two quenches and then project the auxiliary system onto diagonal places, plus or minus. So what you see here is exactly this conditional work distribution conditional on obtaining the auxiliary qubit either in plus or minus result. And this is taken in the limit of rapid quench. So that means that the change of the Hamiltonian is higher, strong, like faster than the typical energy of the spin. And usually when we have a rapid quench, we have something which has a very large degree of irreversibility. Because if you have something which is very slow, adiabatic, it's usually reversible. Now, what you see here is a difference between the three histograms. The one to QISS the histogram is a classical mixture of the forward and backward process, where, for example, you have half of probability that will have no investment of the work. And the black and yellow parts are work distributions from these extended TPN schemes, conditional on obtaining plus or minus result. So we see that we get some interference effects because we don't have the same as a classical mixture. And these interference terms can actually either sharpen, in the case of the plus results, or flatten, in the case of minus, the work distribution. So if you think that the degree of reversibility is given by the probability that you have zero entropy change, then although the classical mixture and each individual have certain degree of reversibility, you can, by this interference effect increase or decrease the probability for zero entropy change. In that way, decrease or increase the degree of reversibility. In a sense, you can fake situations in which you have two individual processes, both of certain degree of freedom, and through the interference effect, make a new one which has higher or lower one. This is another way to state the same. What you see here is a work distribution as a function of h bar omega. So h bar omega is the largest possible work investment, or because in this case, entropy is just the work investment. The free energy is the same in both cases. The h bar omega is something which is also proportional to the entropy with the temperature constant, Boltzmann constant. So what you see here is that is several curves. So let me just introduce each of them. The yellow curve is the curve where you have an entropy increase in forward process exactly h bar omega. So that means you start with some z minus, which has a zero energy, then you have a forward quench, and then you end up with the state that has h bar omega energy. So indeed, h bar omega is the work invested in that case. So this is the yellow curve. And then you have the two curves that is, violet and bluish or turquoise, which corresponds to the conditional this interference, so to say, probability distribution for the same change of the entropy. And what we see that if this is two curves, and the last one, this greenish curve, is the sum of the two. The sum of the two which are conditional one. And now what you see is that when h bar omega is much larger than kt, and the kt is this vertical line, so in this area, then summing up the two interference curve gives the same value as the forward process, as the probability distribution for the forward process. That means that if we have an entropy change which is much larger than kt, not only that we have no interferences, but we effectively project the process onto the forward direction, because then the sum of these two results corresponds exactly to probability distribution of the forward process. But again, we didn't project the process actively onto the forward. It's just that measurement of entropy effectively projects on the forward process. However, if we have situation around kt, this is not anymore the case, and we have these interference effects that I introduced before. Okay, with this, I'm coming to the conclusions and outlook. I think that I'm a little bit over the time. I hope that we will have still some time for questions, and there were questions in between as well. So the questions that I have addressed in this talk are the following. How well-defined thermodynamic error of time is established for such superpositions? And I try to argue that this is through quantum measurement of entropy. One could speculate that in nature, maybe we spontaneously can have situation of superposition of different thermodynamic error of time, and that environment or experimental situation then prefers a certain, if you want, measurement basis that is related to the measurement of entropy, or in that case, simple, this will be the measurement of energy, which then projects such superposition into the states of a definite time directionality, and any further attempt to build up again superposition will be suppressed through this environmental selection. This is highly speculative. I didn't say anything about that, but I like to think about these terms. Then, what is an operational signature of this superposition in this work? This was work distribution, and we showed that it has no classical counterpart. It's different than any possible classical mixture of the two processes involved in the superposition. And finally, it turns out that it could be useful for something. I didn't have time to talk about that, but interference effects obviously can influence the work distribution. And sometimes maybe you don't like certain values of the work in the work distribution, and you can design phases such that you reduce these undesirable fluctuations in the thermal machines. I don't know how realistically this practical advantage is, but you can play around with this as well. This time I wanted to concentrate more on the fundamental aspects of our research. And with this, I thank you for your attention.
Thank you, Časlav. Yes, thank you for the great talk. So we went a bit over time, but we also interrupted you a few times. Usually we have a commentator, although today, because we arranged this a bit in the last minute, we don't. So I will ask one question, hopefully giving you an opportunity to elaborate a bit more on your last point, if I don't get this completely wrong. And then we will open to discussion with everybody. So, yes, regarding of whether it is useful for something, I mean, it's pretty striking, the implication. I'm wondering if I'm not understanding something well, though. So in your paper, I see that you have proven, if I understand well, that the black line in the histogram is something that cannot be achieved with a classical mixture. So there is a quantum advantage. And you note that we proved that our findings can also lead to practical implications, paving the way for their adoption in more general context for enhancing the performance of standard thermodynamic engines. Which, if I understand well, maybe this is not yet very well quantified, how much useful this might be. Now, a standard thermodynamical engine is a heat engine, right? So you want to take heat from a hot reservoir to a cold reservoir. You cannot do that without putting some work in the environment. And then there is something called, if I remember well, the efficiency of this, the Carnot cycle efficiency. And this all comes from the second law of thermodynamics. Now, if you're saying that this efficiency can be enhanced, does that imply that the second law of thermodynamics does not apply in this situation? which maybe is the case because it's not a fully macroscopic system. You're quantum manipulating 1 degree of freedom, but I'm not sure if I'm getting this right or wrong. Does the second law of thermodynamics apply to this whole process?
Okay, so I would say, at least in the, so I wanted to show this machine, but let me first answer your question. So I would say that the second law is correct up to the fluctuations, in a sense that the best, in my view, quantification of that is the fluctuations theorem itself. And so, as you said, in a macroscopic state, I simply have fluctuations that point on, if you want, violation of the second law. Now, what we do is only to, first of all, to show that if you go into very in macroscopic case, in a sense, when you have not with a size, but with an entropy change that is much larger than 1, or work invested much larger than thermal fluctuations, you do have an agreement with the second law, I would say. But in the regime where there is, where we cannot, when we have fluctuation, thermal fluctuation, that we can play around with superposition and phases, fixed phases between the forward and backward process, and in which we can change the probability distribution. So in the regime, basically, where we can say there is no strict entropy increase or decrease, we can make use of this interference. And so I would not say, I mean, I would say even in a classical case, you have this statistical violation of the second law. It's just that here you have, in addition, interference effects.
Right. What I would find very striking is if by quantum manipulating 1 degree of freedom, the control, basically, you exploit the fluctuations. That I understand, but if you actually get a practical advantage, like in practice, that would be striking, right?
Yes. So maybe I can say something about this. Is the machine that we have in our work. This is a simple machine with 2 qubits and 2 thermal reservoirs. And what we superpose, it's a heat engine and a refrigerator. Okay, and so what we have here is that in the first one, we have something which is a heatman, in the upper picture, a heat engine, and the low picture, we have a refrigerator. So what we have is at the beginning, some qubits in a thermal equilibrium with environment, and then we make a swap of these qubits and extract some work and get heat and get working as a heat engine, whereas in the lower case, it's a kind of it's investing some work and working and using this as a refrigerator. Now, so this is what exactly I said, heat engine. You extract some work, which is a negative, out of the heat current from the hot to the cold reservoir. And here you have a power-driven refrigerator, where you extract work from the cold reservoir at the price of the input work. I mean, these are the things that are used in and established as a heat engine and power-driven refrigerator. So what we did is we superpose these things in the way how I described. And so here is kind of advantage. So here you have a distribution of the invested work and heat exchange with the cold reservoir. And if you have a heat engine and a refrigerator, you always have the same 3 points. But the difference between the first and the second point is that you have here a little bit larger negative work. So you extract some work, where here you have a less of that. but the case of the positive one is larger as compared to the heat engine. Okay, so the difference between these two peaks in these two cases is what defines a heat engine or refrigerator. In both cases, you have the 0 point very high. That's where you have no work, no extraction, no investment. So you can say, well, this doesn't work neither as a heat engine nor as a refrigerator. Now, if you look at the superposition picture, you can actually, in the last one, suppress these cases. So maybe it's not a very useful machine because, well, you usually either want a heat engine or a refrigerator. But if you play this game and say, okay, I want sometimes a heat engine, sometimes the refrigerator, but in no cases I want that the machine doesn't work at all, then this last kind of graph will be useful. I am not saying really useful in the terms of people that really can maybe use this for thermodynamic, but you can artificially, at least in our example, tailor the rules of the games such that you are punished whenever your machine does not do anything. And you don't care whether it works as a heat engine or refrigerator. In that case, there will be advantage. But as I said, this is just the first example, and I hope there are more really realistic examples.
Great, thank you. Thank you, yes. Okay, so we are moving to questions from everybody. There's two people that raised hands. It's Onyan and then Carlo. Onyan?
Hey, thank you, Časlav. That was intriguing. I have basically two questions which seem maybe related. So my first question is really rather general and a bit provocative. Is this really a reversal of the thermodynamic arrow here in what is proposed in this thought experiment or even a real experiment? I don't know. Essentially, is it correct to say that in a way you presume standard causal quantum theory in both of these, in the analysis of both branches of the superposition?
Yes, I think this is a very good question, and this is the one that I also pose to myself. I think there is a similarity with, if you want, and people are mostly familiar with this, with the switch, the physical realization of the switch. We talk about superposition of causal orders, and yet we realize this in lab, in which you have kind of laboratory time, according to can unfold this sequence of events, that nevertheless, if we defined events through the operations, could be shown to be in superposition of orders. So I guess this is similar as here. If you would like to realize this process, you will realize in some lab in which you have a laboratory time, and basically this picture that I had is nothing else as some kind of a circuit picture of this process in which the time goes from left to right. And so I think that there is some kind of external time according to which you make superposition of thermodynamical errors of time. And I think, again, you can maybe introduce some criteria according to which you define thermodynamical errors of time as, for example, increase of entropy, and unambiguously show that this here, you don't have a classical mixture of it, just like in a switch case. I motivated the whole thing as an attempt to somehow go beyond assuming that time has some objective notion in quantum theory. But I said that I cannot answer this question, I think, but I can answer a smaller one, or a less significant one, is the one of the special case of the thermodynamical error of time. Having said this, I think here is something about directionality of time, not about the time flow. So I could use this laboratory time to kind of control these unitaries. But the notion of the directionality of time, that's my now personal, I really don't know any better than the thermodynamical one. I think that there is something very profound when we say that we zoom into microscopic scattering and we don't have a notion of time. And I think this is the real thing, not just apparent thing and there is a flow of time. At least, okay, for the people inclined to operational approach, maybe they will say that this is, so there is a time according to I have to control these unitaries, but I think the notion of the directionality is really somehow connected to thermodynamics. And this is here the attempt to put this in superposition.
I agree it is related to thermodynamics, although I have a different view on where it comes from, and I think it has a little bit to do with what some people call causality, like Kiribella's definition, and that I think
you
is
mean like
a
signaling.
Yes, it's a more general thing that holds for our world, at least in the vicinity of our world. And okay,
yeah, this is very. I agree with you. I think,
yeah, but I think it implies the thermodynamic error in a certain sense, in which here, for instance, if one were to do this experiment, perhaps it's not an actual reversal of a thermodynamic error, because maybe it's a simulation. I don't know. It was just I wanted to hear your opinion. I have to think actually carefully about this because I'm not sure myself.
Maybe in some very exotic background time, one can not think about this process superposition as unfolded in a linear laboratory time. But this is, I think, somehow not essential for the part of this story.
I have the feeling that the interplay between there is this dual notion, states and effects, which somehow here everything is done at the level of states, and I have the feeling that the thermodynamic error normally also has to do with this special form of the future boundary conditions that we have, which is linked to causality and so forth. In that sense, this is more like mimicking something, but not quite the true reversal of a.
Yeah, so here the notion of signaling is not relevant. It was purely entropy change.
Yes.
It would be interesting if one can maybe go beyond that.
Right. Though maybe a post-selection might actually be required to actually do this in our laboratory.
Yeah.
Within our world. However, another question, I'm not sure if it seems to me a little bit related, and again, this is perhaps based on my inability to immediately grasp all the details of your work, is this superposition, controlled superposition of the different processes. If we take, as I understand it, in the philosophy here is that the direction of time is determined actually by these fluctuations, and by the increase of entropy is what we shall call the direction in which we call positive. Now, somehow intuitively, in the different branches of the superposition, time flows according to your analysis in the different directions, then isn't it natural to expect that somehow, by the very definition, it should kind of factor out, and maybe what is actually going on is really a superposition of the order of the two, is a controlled superposition of the order of the two measurements, like in the game with which you started to motivate that. If we take that really the direction is something that you would infer in either of the branches. I mean, maybe we can just take that out and say, well, here is the direction, and actually what was superposed is the two orders in which we were calling these measurements, 1 and 2, or something like that. Or is that not?
Maybe it is enforced like that, because you get only 2 results. Well, if the 2 results indicates a large entropy positive change in one, then they immediately indicate a large negative entropy change in the other. I would say that's why they are with opposing entropy change and opposing errors of time. And it is the trick, technically, to just require two numbers out of this superposition, and on the basis of the two numbers, define the entropy change. And they are constructed such that if you have a very positive value of entropy and compare these two separately, then you say, oh, the first one is very likely and the other is very unlikely. And so when you make this superposition and you measure entropy, the result will be random. If you get a very, it will be absolutely random. But once you get it, if it's positive, it will be in agreement with the forward, and if it's negative, it will be in agreement with the backward process. So it's really, in a sense, like a superposition of position of a particle. It's a completely random. Once you project, you know where it is, in a sense. But this is the same here with the error of time. But it's enforced by this trick that you have two numbers and in suitably choosing the forward and backwards process, such that when one is very likely, the other is very unlikely. But which one is which is up to your definition. Sorry.
I'll just wrap up. I imagine maybe if you were to store the outcome of the first measurement in one of the branches on one probe and in the other branch on another probe, such as to make them match cross, like in the first branch to be stored on where the second measurement is stored in the branch, then probably the thing is going to figure out you're going to get. So
I don't know if I lost the last few sentences.
Well-defined. Yeah, sorry, it's probably the connection. I think probably here, because the probes or the where you store the measurement outcomes is different in one and in measurement one and in measurement two, then of course it's kind of you see a difference. But if you were to store also the outcomes of the first measurement in the first branch of the superposition on the same probe on which you store the outcome of the second measurement in the second branch, maybe then you get an error of time going in some well-defined direction, entropy increasing, and then it's like a superposition of something else controlled by the probe.
Okay, I have to think about that. But it's very essential that the coherence is preserved in these process measurement. So it's really encoded in the ancilla that you read out at the end, because you don't want that you break the coherence by measuring qubits. Like a photo detector will not work here. You should really couple to the ancilla.
Okay, thank you.
Thank you. So, Carlo, would you need the slides? It's customary at this point to
No, I don't need the slides.
Okay, so Časlav, should we turn off the screen sharing?
Okay, good.
So we can see each other.
Is this like that? It's good?
Yeah, that's perfect. And so I'm giving the, I will give it now to Carlo. Let me just say that when somebody asks a question, it's natural, there are follow-up questions. If you want to unmute and comment on something, if it's related, feel free. Carlo?
Yeah, thank you. Thank you, Časlav. This was very interesting to follow. I have a technical question and a technical point and a conceptual point. So let me start from the technical one. There's something which bothers me, which is the following. The phenomenon you're talking about depends on an interference term between two processes. The question is the following. All the setup in which we've been talking about, you always need something you have called a thermal bath, which has a certain number of degrees of freedom. So the question is why doesn't happen what I would expect, but maybe I'm wrong, that there is a suppression of the interference term due to the fact that sort of in the two branches, the states of the thermal bath are sort of nearly orthogonal. So I
know what you. I think.
Why is not very small, given that you call thermal bath?
Yes, I think this is a good technical point. So indeed, this interference term have two possible states of the bath, and now depending. This phenomena is of okay. So this phenomena is dependent on the purification, in a sense, and so you have to take care about the choice of the environment in order to see the interference, because otherwise, if there will be orthogonal states and then you trace out the environment, this will give just a mixture. So it very much depends on that, and so. In the general scheme, in which we talk about effective projection, we didn't need to specify overlap between the environmental states in the two branches, because this is independent of that, and this is not basically interference phenomenon. We just say that if you observe very large change of entropy, you will project on the other one or the other error of time. So you anyway want to kill every interference. So there it was not necessary. In the second part, when we talk about interference phenomena, there we should choose very particular environmental states such that they don't have they are not fully orthogonal in the two branches, or they are maybe the same or partially overlap. And this will influence the strength of the interference. If they were totally orthogonal to each other, we will not see interference.
But it's a funny trade-off, right? Because to get interference, you have to control the thermal bath, and to call the thermal bath, you have to not control it. So you're sort of in between. You want to have the cake and eat it too, in a sense.
Yeah. I don't know, maybe you have the same nature of the bath. I don't know to what extent you have to control this, and to what extent laboratory situation will give you the same path, for example. It's not obvious to me. Yeah.
Okay, but
this is an important point. Yeah.
Let me go to the conceptual point, and I connect also to Ognian question. I think I agree with everything you said, conceptually, totally. The question is perhaps, maybe so what? In the following sense, you started by saying I'm talking about the arrow of time, and I'm defining the arrow of time in terms of the thermodynamical arrow of time, the increase in entropy, in a more precise sense that you have specified, because there's also work here. I'm with you 100% that this is the interesting arrow of time. In fact, I strongly believe, sure, to the extent inside, which you are not never sure of anything, that this is the arrow of time, in the sense that all the others are just a consequence of that. Ogden said he doesn't believe so, but I think when he says so, is wrong. I mean, many other things he's right, but I think is that what we call the causality or causal influence is just an effect of the same thermodynamical thing. The fact that we can store an information for the future and not for the past, which is a thermodynamical thing. So great. We're talking about the arrow of time, and we are correctly identifying the arrow of time as the increase in entropy. And now also you're correctly creating a quantum superposition of two phenomena in which one time goes in one direction, time goes in the other direction. Perfect, great. But look, suppose, what has quantum mechanics to do with all that? In a sense, I can be in a laboratory, and in the sense in which you're talking about, I can have a little experiment here where there's something happening, which time goes forward with respect to my age time, and next to it, another little experiment separated, no, totally independent, in which time goes backward. So I have both of them, okay? They're both happening here. Time goes this direction, time goes in the other direction. I agree, you can always have the same thing going in superposition of the two. Is interesting technically, but conceptually, for what regards the nature of time, it seems to me that the key interesting you have said is at the beginning of the talk, when you sort of told all of us, look, if you go in the small, classically, precisely because the second law of thermodynamics, as you very nicely answered, Marius, it's not an exact law of nature. In fact, it's not a law of nature at all. It's just something that happens when there is many degrees of freedom and there is initial low entropy, so it can be violated. In fact, it is violated. It's violated by de facto every time there is a laboratory in which you see molecules doing things, which if you compute work and free energy, you see it goes the wrong direction with respect to the second law of thermodynamics. So good. So in nature, provided that you isolated things enough, you see the arrow of time, the only arrow of time which makes sense, which is the thermodynamical one, going back and forward. Once this is understood, this is significant for what we mean by time. Very good. So we understand that the arrow of time is a macroscopic phenomenon, is a contingent phenomenon for low entropy of the universe. Then quantum mechanics follows. If this is true, it's a great point about the nature of time, which I think is totally true. In classical theory, then of course quantum theory follows up. So obviously you can have a superposition of one phenomenon and another phenomenon, in which in this precise sense the arrow of time reversed. So I don't think it's anything mysterious about quantum theory, anything mysterious about the arrow of time quantum theory. It's just something extremely surprising for our normal intuition, the fact that indeed the arrow of time is thermodynamical, it's statistical, it's approximate, it goes wrong in when you have a small number of degrees of freedom, and is contingent to the fact that we live in a universe with past entropy. So would you disagree with that? Where?
Oh, I won't disagree, but the question is always what to do. So one of the motivations for this is really to look at more and more concepts that previously you thought they might be in a certain classical sense objective, and to weaken that. And now it could be surprised or not being surprised. We are not able always to do a truly new work that cannot be extended from quantum theory. So one of the ideas of these many works in quantum foundation is to extend the quantum theory to larger and larger domain and different concepts. But now, when you say I have in the laboratory two processes, and one with one direction of thermodynamical time, and the other with the other one. I think what you actually do, you make a relative observation. You said that one is forward and the other is backward, or the other way around, with respect to some other phenomena on which you apply thermodynamical error of time. So it's not so obvious, well, I think, this example, because if you would have an absolute notion of the flow of time, then I would say, well, I have these both thermodynamical errors of time back and forward with respect to the absolute notion of the time flow, a directionality of time flow. But now, because you don't have it, and at the end you you rely only on thermodynamical time, even for this statement, by looking at some other phenomena that are maybe macroscopic, for which you have good belief that this is the direction of time, you say these two are in the opposite order. And so it's not then obvious that you can go beyond that and look at a true superposition of thermodynamic errors of time. I don't know whether I was clear now, but your example was showing that, well, it should not be strange what we're doing, because I can have both thermodynamic errors of time in my lab in the different processes. So they coexist in this world. Whatever coexists can be put in the superposition. But what I want to say is that this coexistence of these different thermodynamic errors of times were also defined to your adapted thermodynamic error of time. Whatever you looked around your world to say that one is in direction of this or opposite to it. And so the question again arises, can I put this grand thermodynamic error of time that you used at the beginning, hiddenly, implicitly, in the superposition or not?
So you're saying, the question you're raising is, can I put the larger hour of time?
At the end, can I think about really...
Can nature have put the larger, which is what you said in your last slide, your speculation?
Somehow, yeah.
Yes, Carlo, so if I can sharpen the comment I made before, I mean, I agree with you that if you're looking at microscopic degrees of freedom, there are fluctuations both ways. And that's what Časlav was saying too. If you have, if the work, sorry, the change in entropy, if it was of order 1, then you actually lose the arrow of time. But I think what Časlav is claiming is that by quantum manipulating this 1 degree of freedom, you can get a macroscopic change in the work on macroscopic systems. And that's what is striking. He's not talking about, I'm going to gain an advantage on an entropy change that is irrelevant in the macroscopic world. He's saying that maybe there is actually a macroscopic advantage. And that's what I found striking.
I mean, macroscopic.
I don't think Časlav is saying so. I mean, I don't think Časlav is saying I can use all that and macroscopically create an engine.
I think, first of all, I really have a little bit. I never thought that quantum theory has anything to do with macro. Quantum theory has a claim of ultimate validity over all scales. That still has to be proven, of course, but this is the claim. So this macro, that's why during my talk I said this is relative to the fluctuations, whether this is a large or small system. This is a secondary. It's in practical terms, it's always like that. It's related to the micro and macroscopic physics situations. But if I increase the thermal fluctuations, I can have truly macroscopic things where I will not be able to define the error of time.
Right. It's quantum, and you can have truly macroscopic classical situation in which the error of time is there, which is very simple, right? They just take thermal equilibrium, there's no error of time, period. I mean, there's no memory. In thermal equilibrium, you cannot measure something and then store it for the future because there's no memory. There is no way of storing things.
Yeah.
whole thing you need to be out of equilibrium. So, so no, I see what you say. So the suggestion you gave at the end, your speculation, is very interesting. You say, well, maybe let me put it more strongly that you dared doing. The second law of thermodynamics is completely comprehensible once we have understood why entropy was low in the past. Well, maybe entropy wasn't low in the past. It was a superposition of all things which was projected on one particular branch, and once we're there, and we stay there.
Yeah,
I
was never really convinced or understood really what people mean, what this was entropy in the past or low. Under which measure of entropy was this low?
Yeah, I think, I mean, you're trying to open an open door if you try to convince me of that. I mean, I'm very much convinced of that. So classically, the phenomena we observe, de facto, we see entropy increase. We see low entropy in the past with respect to the coarse-graining that we're using. I agree.
Okay, so with respect to the coarse-graining, that's I'm with you. Yeah.
Which is a very key with respect to. I mean, entropy is only dependent on the coarse-graining, or distinction work versus which is the same thing. Okay, I think we basically, I don't disagree with what you said. I think there's no disagreement on that. I have to apologize with everybody. I mean, the University of Rome has asked me now to do something, so I have to leave you. I'm very sorry because I wanted to.
Well, it's great having you here and chatting again, and thanks for the questions.
My own country, sorry.
Sure. Okay. Bye-bye.
Okay, so we have Alexei, Alessandro, and Dink. I'm not sure who was first of Alexei and Alessandro.
It's an indefinite order.
Okay.
So you have to collapse it, Marius.
Yeah.
Go, Alexei.
Okay, thanks. Yeah, good to see you. Thank you, Časlav. So Carlo asked you something like, what does quantum mechanics have to do with that? And I would like to ask a complementary question, which is, what does thermodynamics have to do with that? So imagine instead of talking about unitary evolution, you talk about quantum Turing machines. Instead of these gas with a piston, you have strings converted by these Turing machines, initial strings into final strings. And so instead of thermodynamic entropy, you will be talking, let's say, about quantum Kolmogorov entropy. Can you write exactly the same kind of formalism for that?
Okay, this is a nice question, and which I'm not sure I will be able to answer because I don't know good literature even on fluctuations theorem and quantum thermodynamics. But I was also thinking about going beyond deriving or thinking about fluctuations theorem in the way I presented it, and also going beyond thermodynamic entropy, what you are referring to. And I believe if you can have a meaningful definition of the thermalization in terms of algorithmic complexity, I think this is possible to be done. And I think there is something very universal in this thermodynamical, in the fluctuations theorem, something which is related to resource theories and going out of the free states, which are thermal states, and the probability ratios between forward and backwards process. So I saw derivations that are really very general, but none of them referring to the algorithmic entropy. That will be certainly very interesting to see. So I think it goes beyond thermodynamics in narrow sense.
Okay, cool. Thanks. That's it.
It's Alessandro, if I may ask my question. Thanks for your presentation. I was thinking if this forward and backward arrows time interacting together was reminding me a lot of two-state vector formalism. And in this context, I was wondering also if the idea that at the microscopic level, we are actually losing this forward and backward arrow of time doesn't lead to a kind of thick present concept in which if we go at the quantum level, we have a kind of thick present where forward and backward arrow of times are somehow merged. And then the resolution of this thick present evolves, leading eventually macroscopically to a thermodynamic arrow of time, but at the quantum level, still it's a superposition of forward and backward with different probabilities that following the increase of entropy and the need for work, eventually at the big scale goes in one direction, but still the thickness of a present due to the indefinity of the arrow of time at quantum level can be considered in this picture?
As we discussed now also with Carlo, I think this indefiniteness, but of classical type, is there already in classical case. So if you're at the level of thermal fluctuations, you cannot distinguish between forward and backward very well. The quantum mechanics tells you a little bit more. That whenever you have some indistinguishability, you can put them in superposition and make kind of interference about that. So the thickness, I think, is there already in classical whenever you are around or below thermal fluctuations. I wouldn't say that this is genuine quantum phenomenon. Quantum makes a little bit more dramatic in the sense that you can make superpositions, and I'm sure one can maybe derive certain no-go theorems in which any other assumption that the thermodynamical time is well defined can be disproved. But I wouldn't say that the thickness of this presence is purely quantum.
No, I was not suggesting it was purely quantum. It could also be a greater scale, but I was just trying to see if you also see this kind of thickness due to the super.
Yeah, I feel that there is, at least if you time defined as through entropy change as in thermodynamics, that there is a region around which we don't have well-defined time in that with this definition of time. Okay.
Marius, should I ask a
Yes, go ahead, Dink.
Hi, Časlav.
Hi,
thanks for the interesting talk.
Thanks.
So my question is about, it's more of a broad question. I'm interested in our laws of fundamental physics. Do agency and consciousness play any fundamental role? There's this debate that, in one position they shouldn't, because we're just collected excitation of quantum fields, of fundamental fields, and in principle we can give up these notions of agency and consciousness. These are emergent notions, and they're not necessary in our fundamental laws of physics. But in another position, maybe they do, especially if you think of quantum theory. You think of, say, the Copenhagen-ish interpretations. So broadly, I'm interested in this question, and in the context of your talk, I'd like to connect this question with the first point of your summary slide. You mentioned something like maybe there's a decoherence that plays a role in obstructing microscopic superpositions of arrows of time. So I wonder, for this decoherence mechanism you have in mind, maybe for future research, would you say that it's okay for this decoherence mechanism to work without agency, without consciousness, or is consciousness necessary?
Okay, that's a very hard question. And I'm not sure I would like to even say openly my speculation about that, but I don't know about consciousness. This is too hard. But I can maybe say something about agency. And then when I said about this decoherence, I intentionally said both things. I said measurement apparatus or environment, such to cover both the group of researchers who are inclined to think about agency as very important aspect of research, and those that want agency out of the game. And I didn't make my mind yet, but there is something, and this is really intuitively now, that when I look at the gas and I see that all molecules on the left hand side of the vessel, as compared to when they are spread all over, is something which catch our attention immediately. We see they are totally distinguishable situations. But imagine now the situation which is physically, as we use in physics, equally distinguishable. We have in both cases gases in the left half of the vessel, but in one they are a little bit shifted. They are maybe for the dimension of the diameter of a molecule shifted to the left or right randomly. This is even classically distinguishable, maximally distinguishable. There are aims to prove that these are totally distinguishable situations, just as the first case. But this distinguishability, where in both cases they're on the left-hand side of the vessel, are not something which we catch with our eyes immediately. And I think this is not an accident. The way how we organize our world around us and describe is coarse-grained. I think maybe Carlo would like that, but such that we somehow think about roughly something being similar or not, according to coarse grain that we choose, and see immediate increase of entropy, whereas the other changes are not an increase in entropy, although there are changes that are equally dramatic, distinguishable in both cases. So what I want to say is that it seems to me that it could be, but this is really now very, very, very speculative, the way how we organize and observe things and try to make sense about it, maybe even some preferences towards measuring entropy around us. And from that, maybe extracting then error of time. But this is now really extremely speculative. I wouldn't like to be quoted on that.
Okay, I wouldn't. But maybe we can have some more private discussions.
Sure, I would love that.
Thank you.
There are no more hands raised, but if anybody wants to comment or make a question, feel free to unmute yourselves.
I have a question, if it's okay. I did not really follow through all the technical details of the presentation, but I think I understand the gist of the physical situation. It's kind of, and it's okay. I have no problems with that. My question is about the idea, the concept of the arrow of time is connected through to the notion of entropy in the standard contexts, classically at least, by assigning a low entropy state to the initial condition and the high entropy state to the final condition, and then seeing what happens in between. There is evolution. So the notion of the time flow, the arrow of time, is somehow encoded in the boundary conditions of the problem that you're looking at. In the sense that you have some, I mean, classically at least, you have some equations of motion, you put some boundary conditions like the initial and the final condition, and then you look what happens. And then you see that time flows in one direction or another. Now, is there a way to understand what you have been doing, your kind of the setup that you're looking at with the superposition of two different time directions, in those terms, in terms of specifying a boundary condition initially and finally, and distinguishing between those, or not, or is it somehow outside of
yeah,
that?
I think, yeah, but well, at least in these cases that I was considered, if I understood your question correctly, this is also, I'm not sure, but there is some kind of well, chosen boundary condition, if you want. So we start with the thermal state, then we move out of the thermal state, and then we let this thermalize again. And so thermal state is really something very special here, in a sense. And if you would have really just arbitrary initial conditions, you might not end up with any asymmetry. At the end, you need some kind of asymmetry. I'm talking not about superposition, I'm talking about even a one way. You need some kind of asymmetry or in order to even claim that there is time directionality. So I think there is implicitly there in the game of time directionality that you start with the thermal state in both cases. I think this is a very important element. And somehow, maybe the way to weaken it is to put in the superposition. But otherwise, I think the fluctuations theorem would not have a preferential directionality. Maybe it will be more reversible if you would not. But there are works that go beyond the thermal assumption of thermality at the beginning, at the end. I'm not that familiar with this.
Okay, thank you.
Great. We are at almost 2 hours. Don't know if Časlav has any more time, and if anybody else has anything that they want to say. Okay, so otherwise, I think this is a good time to wrap up. And thank you very much, Časlav, for this great lecture.
Thank you very much as well for being here and for the invitation. And I guess we see each other only in January.
Yes, after the holidays. So happy holidays to everybody.
Yes, happy holidays also from me.
Bye-bye.
Okay, bye-bye.
Ciao, ciao.